Now the question is, let's consider how to do this. How to modify a GAN such that the inversion that we just spoke of is possible. Okay. So first let us look at an approach called bidirectional GAN or bi-GAN. Okay. Now in a bidirectional GAN, so in a naive GAN, what happens is that we have two neural networks, right? In a naive GAN, so there are two neural networks. There is the function g theta of z, which would take a vector from normal distribution and map it to the data distribution, and there is the discriminator network that would take points from data distribution and maps it to 0 1. This is what we saw, right? So in bi-GAN or a bidirectional GAN, in addition to these two functions, okay, in addition to the generator and the discriminator, there is another function called the encoder network or the inverter network. Inverter function. What would this inverter function do? I mean, one can easily guess. Let's call this E phi. This E phi would take samples from the data space and maps it to samples from the input Z space. Okay, that is what the encoder function would do, and it is parameterized by another neural network phi. Okay, so if I write it diagrammatically, so we have a generator function So this generator function would take data from Gaussian distribution and maps it to the data distribution. Okay, and here there is, of course, there is a discriminator that is used during GAN training. And this would take data from either x or x cap and map it to the range 0 1. In a bi-GAN, there is another network which is called the encoder network. Okay, let me write it a little far away so that another neural network which is called the encoder network that would take data from x. So this x comes from a px, and let us call this E phi of x, and this would give you a z. Okay, let us say that this has let me call it z cap, and this has a distribution p phi of z cap, right? So this is how one would construct a bidirectional GAN. Now the question that is to be asked now is, how do we ensure that this encoder network gives the z that corresponds to a given x? right? So there is no mechanism in a naive GAN training that would ensure that this encoder network would give you the Z or the input vector corresponding to this given particular X. So how do we ensure that? So in the BiGAN formulation, the idea that is done is the following: the discriminator, so in BiGAN, the discriminator dw is designed to classify between the data tuples of the form x, g theta of z and z, e phi of x. Okay, so what is being done here is the following: that in a naive GAN, what do? The discriminator discriminates between x and x cap, right? So in a naive GAN, DW network, DW classifies between we have x and g theta of z, which is also x cap, right? The points from the true data and points from the real true data distribution and the generated data distribution, right? That is what a discriminator does in a naive GAN. In a BiGAN, instead of classifying or discriminating between x and g theta of x, the classification is between the tuples. I think there is a mistake here. The tuples of the following sort. So we have x and the corresponding output of the encoder network, and we have z, okay, and the corresponding output of the generator network, right? So look at this: the tuple, one of them is from the data space, the other is from the input vector space, and here, okay, maybe the order has to be redone. So this is from the data space, g theta of z is from the data space, and z is from the latent space. So the question that we are asking is, given a particular data point drawn from the true data distribution, I should write that. So where x is sampled from px, and we have e phi of x, this is sampled from p phi of z, okay, and z is sampled from normal 0 1, and we have g theta of z is sampled from p theta. Okay, so these are the, okay, so we've been calling this z cap. Look, these are the four distributions that we have here. So the question that we are asking is, given a data point from the true data distribution, look at what is the output of the encoder network is or the inverter network is. So group them together, that becomes a pair. The other pair is the generated data. Given a particular z, look what is the generated data. Okay, now what do we want is that the distribution of the pair of these two random variables and the distribution of the pair of these two random variables have to match. Okay, if that happens, then this encoder network would be sampling from the same distribution which the input latent vector comes from. Okay, so that is the idea. So now the discriminator now will not take x and x cap, but will take the pairs of x and e phi of x. This is one pair. The other pair that it takes is from g theta of z comma z. That's it. So if we have a structure like this where we modify our discriminator such that instead of taking data points from the true data distribution and the generated data distribution, it would take pairs of data, okay, tuples of data which would have one point from the true data distribution and the encoded data, encoded input space, and it has points from the generated data and the true input space. Then the discriminator has to discriminate between those two pair of distributions. If we do that, then one can show that this entire setup would learn the encoder in such a way that it can correctly give you the corresponding input data point, input vector given a particular image. Okay, that's the idea. So let us write down what is the objective function that is used here in Bi-GAN. So we have an objective function L by GAN. Now this would contain three parameters: the generator parameters, the discriminator parameters, and the encoder parameters. It has three different parameters here, and this is equal to the expectation of log of dw. Now dw takes 2 points, right? One x and the encoded x, okay, and the inner expectation here, the inner expectation is as e phi. Okay, so let me use symbol. So let's call z cap to be equal to e phi of x. Okay, so this expectation is with respect to z cap coming from, so, and let's also say that this has a distribution given by p phi of z, as we are being saying. So this is coming from p phi, and there's an outer expectation as usual, which is with respect to e of x coming from px. This is the expectation that we anyway had in the GAN formulation. And we have the second term, which is log of 1 minus dw. Here we have g theta of z comma z, where the expectation of x cap is x, okay, let us call this x cap as usual is equal to g theta of z, and that has the distribution p theta of x cap, right? That is what we have been using. So x cap comes from p theta of, so this is nothing but x cap, and here this is nothing but z cap. Okay, so now x cap is coming from p theta, and then there is an outer expectation with respect to z that is coming from pz. And now what is pz? Now pz, now z is sampled from pz, that is equal to normal 0 1. I mean, in our case mostly it is equal to normal 0 1. So this is the loss function that is used in a bidirectional GAN. So now what happens is that this entire loss function, so what is the This is the loss function, and what is the optimization problem that we would be solving here? So we want this entire thing to be minimized with respect to the generator parameter theta and the encoder parameter phi, and we want this to be maximized with respect to the discriminator parameters w. So now what happens, if you remember how the GAN was trained, here all three networks are trained simultaneously, in the sense that start from sampling a particular z, okay, and then you get x cap, pass it through the generator, you get x cap. Once we get x cap, we get z comma g theta as the pair, okay, and we take a particular x from the data set, pass it through the encoder network, you get the z cap. Now take the pairs of g theta z and z and x comma e phi of x, give them to the discriminator, and then back propagate the gradient just the way we are training the GAN. Okay, here the g theta network and e phi network are trained simultaneously using the discriminator, where one gradient passes through the generator network using z and x cap. There is another gradient pass that passes through the encoder network using x and z cap. Okay, that is how the bidirectional GAN is trained. So once a bi-GAN is trained, the generator network g theta star is used for generation, and e phi star of x is used for inversion. Okay, so once trained, what can be done is that given a particular z, the g theta network would generate an image just like the usual generator. Given a particular x, the e phi network would give you the corresponding input vector for this particular x using the encoder network. Okay, that's what happens. So now, why should this work? Let me just tell you the theory as a fact, and then I'll not prove that. So what can be shown is, it can be shown that the optima of the loss for bi-GAN is achieved when the joint distribution between let's call this p e x, or rather p z cap x is same as p z x cap, where p z cap x is equal to the joint distribution between px, the true data distribution, and the distribution that the encoder is imposing. The encoder is imposing a distribution p z cap given a particular x, we have dz cap dz dx, and we have pz x cap is the distribution that the generator is imposing, which is this over x cap. We have p theta of x given z, or p theta of x cap given z. We have dx cap and dz. Okay, so this can be shown that the objective of GAN will achieve its optima whenever the joint distribution between the encoded input and the true data is same as the joint distribution between the true input and the generated data. Okay, and these are the joint distributions that are there. So this is px, I can write this as px evaluated at an x, and this is pz evaluated at a particular z. So this is simply the law of total probability that would write the joint distribution in terms of conditionals and marginals. Okay, so it can be shown. So what is happening here is that if we train a bidirectional GAN this way, that then the joint distribution between the generated data and the input latent, and the joint distribution between the true data and the encoded input vector, or the input distribution is also referred to as the latent distribution at times. So the joint distribution between the true data and the encoded input vector or the latent vector would match. Okay, so when that matches, then what happens is, given a particular input vector or input latent vector, it would generate a data point, and given an input data point, it would generate the corresponding latent vector or the input vector that would have generated this data point using this generator network. Okay, so this is one way to learn or do GAN inversion.